All right, here goes another one of those wonderful math videos specifically about graphing. Woohoo! Well, all the units that we're going to be talking about now, it's going to be from 4.6. And I'm going to be on the journey with you, helping you try and figure out how to find these reciprocal graphs, basically cosecant and secant. And then later, a little bit longer, we're going to talk about cotangent and tangent, how those are related to as well. If you are going to be good at cosecant or secant, you have to understand the fundamentals when it comes to sine and cosine. So if you're struggling with those graphs before you try and tackle this one, it could be a long road for you. So make sure that you brush up on your skills because you should have been doing that over the last few videos. Now, I am one of those firm believers that sometimes if you just get a little bit of a different way to learn something about how to learn something, it might actually help you get the premise of what's going on. So if you've got sine and cosine under control, what you need to recognize is that there might be an allegory to how cosecant and secant are related to sine and cosine, being that they are reciprocals of the original graphs. Now, what does it mean when they become a reciprocal graph? Now, here comes your allegory. I'm going to show you a little video from one of my favorite movies of all time, Galaxy Quest, and we're going to see whether or not you can actually come up with the idea of what I mean by reciprocal graphs after the monster has been digitally conveyed. So here comes the video.
Yeah, Gwen, you got me.
Thank God. Are you okay?
Yeah. Matter of fact, I've got Garignac staring me in the face right now. But you know what? I think I can take it.
Oh. Jason, we're going to use the digital conveyor to get you out of there.
The digital conveyor?
Yeah.
You mean I'm going to be diced into cubes and set up there in a million pieces?
Right.
Well, you know what? I think I'll take my chance with Garignac.
We're getting you out right now. It's perfectly safe, isn't it, Ted?
It has never been successfully tested.
What did he say?
Hold, please.
Theoretically, the mechanism is fully operational. However, it was built to accommodate your anatomy, not ours. But now that Tech Sergeant Chen is here, he can operate it. It was designed watching his motions from the historical documents.
I mean, I can't. I can supervise.
Jason, we're gonna test it.
On what?
How about that pig lizard?
Hey, I'm doing all right with the pig lizard.
Please, Fred, and hurry.
I'm sorry. It's very exciting to watch the master at the controls. The operation of the conveyor is much more art than science.
Stand back, Jason.
What was that?
Nothing.
I heard some squealing or something.
Oh, no, everything's fine.
But the animal is inside out.
I heard that. It turned inside out?
And it exploded.
Did I just hear that animal turned inside out and then it exploded? Hello?
Hold, please.
All right, now I hope you got the understanding of where I was coming from with that video. And the basic premise to it is that when we talk about doing a cosecant or a secant graph, what we're going to actually do is we're going to take the graph and we're going to turn it inside out. And it kind of, in a way, inside, outside. Geez, inside out. Wow, geez, right good here. Inside out. And it's really going to kind of explode. So it is really super similar to what we kind of got there out of that video. Now, to tackle this idea, like I said, you're going to have to be able to do sine or cosine in its own right. Now, I'm going to skip past the review questions, and we're going to talk about the comparisons of, at the beginning of this, between cosine of 3x and the cosine of just cosine x. Now, what is that 3 going to actually do? Well, we probably been understanding that when we talk about the cosine or sine graphs, there were individual values that did certain things. Bx minus c plus d and so forth. Well, the b value that's located in this particular spot turned out to be a period adjuster. And ultimately, if we take that b value and turn it equal to, like 3 is equal to 2 pi over b, which is the period concept, we can cross multiply and solve and find that b is actually equal to 2 pi over 3. Now that means that you're really talking about the value of the period, and that period value is going to be shorter. So ultimately, a graph that's got a 3 in it like this is going to be horizontally compressed. Okay, so we're talking about all kinds of different things that you should basically have a deeper understanding to. Amplitudes, they're related to A. Periods, P, which is related to 2 pi over B. Or if I was talking about the domain or the range, or if I was talking about the phase shift, which is C over B. Or I was talking about vertical shift, which is D. Okay, you need to make sure you have a deep understanding of all those particular concepts before you take a graph and turn it inside out and make it explode. All right, now the first thing we're going to do is we're going to tackle this idea of like, what is cosine of 2x? Let's just graph this idea. Now, as I go down these particular items right here, I'm going to find them all, and then we're going to work on how that graph ends up looking on the graph. Now, of course, the amplitude is 1. The A value is 1. That's in the front of this particular deal. And then we've also got that the period, which is going to be 2 pi over b, which is 2 pi over 2, which is pi. So this particular graph has been shortened, and it'll complete one full wave within 1 pi's distance of what's going on. Since it's a cosine wave and starts high, ends low, and ends high, and keeps continuing, the domain would be negative infinity to infinity, but it would go start high and end up low based on the period, which would be between -1 and 1. All right? Now, little gap amounts will help you figure out how far you have to travel to get to the next really critical point on the graph, and gap amounts are going to be the period divided by 4. And it's always divided by 4 in sine and cosine, or in this case, we're talking about pi over 4. Now, what this gap amount reminds us of is it helps us find out where the maximum, the minimum, where the zeros across, and so forth. Now, when I graph this next piece to this, I'm going to make my graph relatively small, and I'm going to say it's going to start up high, and I'm going to do a little X's here because it's not really the cosine graph that I'm concerned about graphing. It's going to be about the secant that we're really trying to focus on. So I'm going to go a pi over 4, and that would be a 0. Then I would go another pi over 4, and I would minimum out at the actual bottom of the cosine graph at -1. Then another pi over 4 would give me another x-intercept, and another pi over 4 would give me the full period, which is pi. Now, if I keep repeating this idea, I can actually get a couple of waves of what's going on here. Here's a full entire wave all the way up to 2 pi. And we probably should take a look at that just so that we can get an idea of what does the secant wave do, even if it goes forward into its wave cycle or it goes backwards into its wave cycle. Now, what I'm going to graph right here is I'm going to put in a dotted line. And the reason behind this is because as soon as we try and tackle a secant graph, you need to have a parent wave before you can actually do it. It's kind of like you got to have a foundation before you try to make the secant wave. Now, believe it or not, you almost have the secant wave ready to go just by this parent wave that you figured out. So the parent cosine is related to the idea of the reciprocal secant. Now, what we're going to do is exactly like we did on Galaxy Quest. We're going to turn this graph inside out, and it's going to explode. Now, there are a couple of steps you have to first come up with. First, you need to make some asymptotes, some vertical asymptotes that are necessary in this graph. They are going to be where the graph crosses the x-axis at these zeros. You're going to make a set of vertical asymptotes because it's very common for secant and cosecant to be undefined, and these are its undefined moments for this particular graph, okay? So wherever you see a 0 becomes an actual vertical asymptote. So that's going to be the part where we slice it, and the next part is going to be where we turn the graph inside out. So at these maximum points, the graph, instead of it being concave down, is going to completely flip around and become concave up, is what's going to happen. So it's going to go upwards along the asymptote. Now this one, which is concave up, is going to turn around completely and become concave down. And this is exactly like what happened to that pig lizard. It completely turned inside out, and then it exploded. There you go, see? Now you're never going to forget the concept. So the key here is really not so much the secant graph alone, but it's the underlying parent graph of the cosine wave, which creates the secant wave. And it's just a reciprocal or a flipped up, turned inside out version of it. Okay? So it really helps when you do these graphs to find the vertices and so vertical asymptotes, the vertices of the parabolas or the vertical asymptotes. You need both of those concepts, and to find the gap amount, which will always be divided by 4. It's the period divided by 4 to help you understand what secant and cosecant is. Now, therefore, we can conclude a couple of things here. The period for this is always going to be 2 pi over b, just like it was for cosine. The b value represents the number of waves that will be completed during that time cycle. And phase shift will always be the same too as well. It'll be c over b. But you graph the cosine long before you ever graph the secant. And then you touch and flip it over. Now it'll be exactly the same idea for the cosecant graph, which would be 2 pi over b as well. But then the b value still represents the number of waves, and the phase shift is still c over b. But you look at a sine wave before you ever give it a shot. Now, if it turns out that you have a b value that's greater than 1, that's going to actually compress the graph. That's going to compress it horizontally. But if it's less than 1 or greater than 0, it's going to expand or spread the graph. I don't know if that's the right word for it. Spread the graph outwards, and you're going to get more out of that particular period and less waves, but more length out of it. That's probably the better way to state it. All right. Now, here's what we're going to try. I'm going to graph this particular graph of a sine graph, and then I'm going to transpose that into a cosecant. Now, I'm going to pause right here. I'm going to get all my necessary information. You can check to see whether or not I've done it correctly, and then I'll show you how to draw the asymptotes and invert it. Now, I got all the individual values for the amplitude, period, domain range, and the gap. Noticing I'm taking the period and dividing it by 4 to get pi, and that particular number tells me exactly how far I need to travel in a normal sine wave to get to the next piece. Now, in a normal sine wave, we would expect it to start at the origin, and then the next critical value would be pi units away, which would be it going up, so it'd be right there. And then it would return back a pi distance more in terms of another critical value at 2 pi. Now, that's only showing half of the wave, which makes sense because it's only showing that it should be more wavelength in terms of the actual period. We could end up backing the same concept up and get the 1 down for negative pi, and then it crossing at those particular spots. Now, again, a nice little thing to do here is to put in a nice dotted line for your parent graph, which is the sine wave, and then we go forward and we start to talk about how to draw the cosecant graph. Now, first things you do when you draw a cosecant graph is you find those x-intercepts or roots, and you draw a vertical asymptote through the root. Okay, these are going to be the guidelines that the cosecant graph is going to implode and follow along. Okay, now the tops, the mins or maxes, are going to be where the graph ends up starting from, its vertices, and then it's going to draw these kind of parabolic shapes. I don't want to say they're parabolas, they're really not, but they are mirror images of the wave itself, and then as it approaches the asymptote. Now remember, it goes down along that asymptote, not quite reaching it, so you want to make sure you show it with arrows as it's a completed graph going up along the asymptote, and you could see where it's headed. Now that would be a completed graph of a cosecant of 0.5x. All right, you get the idea? Draw the underlying parent graph and then turn it inside out. Okay, again, we're going to try another one of these graphs. I'm going to pause, put in some basic values. And before I do that, let's kind of talk about this graph, this orange graph's important information when it comes to its domain and its range, okay? Because it no longer has the same domain and range of the parent function. The parent function, yeah, travels over infinity all the way along. But when we talk about the domain of the cosecant graph, it's got these vertical asymptotes that break it up. So how are we going to write the domains of those? Now, the easiest way for you to tackle these domain restrictions is basically to say, when is x not going to be in a valid domain? And the very first domain restriction that you can pick out, relatively easy, is to pick out one of them and say, okay, it's going to be 0 for sure. But then that's not going to be the only one. It's got to be something that completely cycles and ends up causing another one to occur. So how far do you have to go till you generate another asymptote? Well, that other asymptote is happening at 2 pi distance away from 0. So we'll say plus 2 pi and then k. And the k is representing a reoccurrence of all the different possible ones that could be out there. So if k is 1, we'll go 0 plus 2 pi times 1, which is 2 pi. That's where that one is. Or if k was 2, that would be 0 plus 2 pi times 2, which would be 4 pi, and that's where the next one would show up. So you have to show it in a recursive kind of domain restriction. Now, the second part would be that it's not going to exist between here and here in terms of the range. It's going to exist from below all the way up to this point, and then it's going to skip through the parent function's range concept and then continue for the other side. So we would say it's from negative infinity up to and including negative 1, unioned with 1 going on to infinity, and that would be the zone here and the zone up there. And that's how you would write the domains and ranges of a cosecant or secant graph. Now, let's give these next ones a shot. Now, in this next graph, I actually pointed out a couple of key features that I want to pay attention to when I first get started. Here, first off, it's a flipped graph, so that means that when I think about drawing the parent function cosine, instead of it going up, it's going to go from a high point to a low point. It's going to start at a low point, go to a high point, and return. So make sure that you're paying attention to the signs in front of there. Amplitude's going to be 2 because of that absolute value of a that's in the front. It's a secant, so I'm going to think cosine. And then I took the actual 0.5 pi and put it in underneath 2 pi for the period, and it generated 4. And you're like, whoa, 4, it's like a whole number. And that's why this particular graph has underneath it, it has graphed values that are integer values as well as not only just doing radian values. So it kind of gives you some insight that it could be a different way. And the gap is the period divided by 4, which is 1, which is actually kind of nice. Now, if I'm going to start by graphing this thing, we would expect it to start low at 2, and then it's going to be completely done with its cycle when it reaches the number 4. Now, I always like to know how far do I got to go before I get finished. Then I can tell where the middle point is going to actually be, and then the gap will tell me where I should put the individual values in between. So it looks like every 1 we get a piece of the graph. So I'm going to go backwards in time a little bit here too. And ultimately, I'll get a couple of waves that I can look at here. Now, this is kind of key because there happens to be something interesting in this particular graph, which is the vertical shifter. Okay, now this vertical shift is going to cause every one of these little x's to not actually be at the -2 and 2 mark, but they're all going to end up being pushed one value up. Okay, now that will not affect where the asymptotes go. It'll just affect where the vertices end up. So we're going to end up crossing and crossing and cross. We'll get all these new crosses in here. And ultimately, before you eliminate the x's, one thing that can be very helpful here with these new x's is to determine that, yeah, even though you moved it up, this was the x-intercept before the vertical shift took place. And that is exactly where the vertical asymptote needs to be placed. So be very careful. Sometimes a vertical shift can make you lose track of where the zeros were. Some teachers will put in what's referred to as a midline. You can probably see that there's a midline that's been moved up. That's the concept. It's been moved up to that spot. And now I can go ahead and I can graph the cosine wave that's really inside here. So I've got this cosine. Oops, I hit the wrong thing there. Let's make sure we go to the black x's. And you can get a little convoluted if you're not careful. This is why we do them all in pencil so that you can get the idea of what you're trying to graph. Now I'm going to go back with my pen here and I'm going to erase these little orange x's because I don't want them to confuse me anymore. And that is where the parent function of cosine is now located. Now what I need to do now is to take that particular graph and I need to invert it and draw the secant graph, which is going to be the inverted version of this, okay? So a thing to be thoughtful of here, a vertical shifter can make things a little bit harder, but if you're just systematic and like, I'm going to draw the regular parent graph, then I'm going to move the parent graph up, then I should be in pretty good shape. Now let's try and write this domain and range, and that's going to be from -infinity up to -1, and I'm going to square bracket that, unioned with, and now those movements have been moved up to this particular point of 3, from 3 to infinity, soft bracket. That is going to be our, that's wrong, that's the range. Okay, let's try that again. This is the range that I just discussed, -infinity to -1, square bracket, union to 3 to infinity. Sorry about that, guys. And then the domain would be wherever I see these asymptotes occurring, you should be in good shape. Now, I always go for the very first one closest to the origin. So I'll be like, x cannot equal 1. And then how far do I have to travel to get to the next asymptote? And that would be plus 2k. And that would get me to the next asymptote that's along the line. All right? Now, practice the next one that's coming up, and we'll see whether the next 2 of them that are coming up, and I will show you the answers to them, and you can try to see if you did it right. Okay, on this example number 4, it did have some things to kind of think about that you might want to watch for. The amplitude being 1, 2 pi over 2/3, which ends up being 3 pi. That's just kind of an odd value that it should be, so you see that it won't extend on this graph. The gap value does give you 3 pi over 4, so it does give you some insight to how far you're going to have to travel to actually get to that midpoint value for the maximum, and then back down to 3/4 times 2 is 1.5. That's why it comes back down here and hits at that particular spot. So work with your fractions carefully. Make sure that you're paying attention to those. The underlying sine graph is drawn right there. I put in the vertical asymptotes where they needed to be. And then I'm going to go ahead and write the domain here. And that would be x cannot be equal to, well, the first place that you get one is at 0. And then the next place you get an asymptote is at 3 pi over 2. And I would say plus 3 pi over 2k. And you would get the actual domain restriction. The range, on the other hand, is going to be another one of those -infinity to -1 included with a union of 1 to infinity. Watch what I'm doing there too. It's really easy to lose a bracket versus a soft bracket, and it's just simple points that you don't want to lose in the long run. Okay, the next graph down has a phase shift, so let's be a little bit careful on that concept. But I'm going to pause again. I'm going to show you the major values that you need. Now, a nice part of this particular graph is the fact that they did a couple of things for you. Negative is going to make it flipped. 2 is going to make the amplitude 2. But they did take the B value out. If you reverse distribute it and pull it all the way out, that becomes just a lonely B. That gives you the period relatively easy. But since you took it out of both terms, you don't have to do a C over B concept. This particular value that's left over here in the end is the phase shift. Just remember that it works just like an H does, and you have to take the opposite value of it to get the phase shift in. Now, this phase shift, as soon as I ever get a phase shift, I'm like, dude, I better get the phase shift in this thing. And since it's a cosine graph and flipped, it's going to start down. It's going to be right down here is going to be the very first deal. Now, the gap amount of pi over 4 is going to ultimately generate the next value on our cosine graph, which is going to be going up. So it's going to be here. And then it's going to be another pi over 4, and it's going to be finally up here at that value. And then it's going to return back like this, and then turn around and go again. Okay, now I'm just going to get a couple of these graphs in here. And ultimately, now I can start to graph the fundamental sine or cosine graph that's really fundamental underneath there. Now, when you look at this, you'll be like, no, gee, that doesn't look like a cosine graph. It really looks like a sine graph. You're absolutely right in that particular interpretation. From this point on, it looks like a cosine graph, but from this point at 0, it looks like a sine graph. And my point to that is that secant and cosecant, if I think about those two words, cosecant and secant, these two concepts are really the same kind of graphs. They're just out of phase. Just like sine and cosine were out of phase, secant and cosecant are out of phase graphs as well too. Makes sense. Their parent graphs are sine and cosine. So ultimately, you could really express this graph as either a secant or a cosecant graph. And in general, they wouldn't be wrong, either one of them. Now, once I've got the underlying graph inside there, we put in our vertical asymptotes at the zeros, and ultimately take the graph and digitally convey it and turn it into its upside down exploded version. Oh, fun. And there you go. Now, domain and range of this one, again, domain is going to be specified by where you see your very first asymptotes. I would say 0 seems like the best one, so x is not going to equal 0. And how far away do I have to go to get to the next one? It should be the gap amount times 2, because it's 2 gaps to get there, plus pi over 2k. That would be your answer for the domain. And the range in this case would be from negative infinity all the way up to negative 2, inclusive with the union of 2 to infinity, soft bracket. And that'll be your answer for example number 5. Now, what we're going to move into last is figuring out how would you actually take the whole concept and think about it in reverse. And you're like, oh man, what are these graphs going to actually be? Well, the key here is to really fundamentally think about what is it you're really staring at? Is at the y-axis, are you really thinking about it being a cosine or a sine wave? Now, since this one starts high on the y-axis, I would probably say that that is saying to me that this is a cosine graph. Okay, so straight up right out of the gate, I'd be like, okay, this has got to be a cosine graph. It'd be like y equals, I'd put cosine out here. Now I'm leaving space right there because I'd ultimately want to put in that the amplitude, which is 5 in this case, goes in front of that. And then the next concept is going to be how far did I have to travel to get to the next full distance of a wave? Now that full distance, which is called the period, is pi. Okay, now I can work that pi concept backwards in the fact that the period is equal to 2 pi over b. And if I put, instead of the word p there, I put the number pi in there and say that pi was supposed to equal 2 pi over b, I can actually cross multiply and solve and get b pi is equal to 2 pi, and that b would be equal to 2 in that particular case. Now I can continue to write my formula. It's really cosine of 2x. Okay? And that would give me the full entire value for that particular function. Okay? Now, thinking maybe, wait a second, what if I had thought that of a completely different way, and I basically thought that the graph was really starting right there? Oh man, wait a second, gee, that's funky. Well, you could think of it starting there and going up and down and back to its returning spot, which would be right here. And now it would not be a cosine wave, it'd be a sine wave. But that sine wave would be out of phase. Y equals, it's still got an amplitude of 5, it's still got a sine, it still has 2 as its value, and I'm going to put that 2 on the outside because that'll make it a little easier. 2 on the outside, and then x, but if I move it over here, it looks like it's been moved over pi over 4 in the negative direction. If I go plus pi over 4 like that, I can write it as an out of phase sine wave. Now, which answer is really correct? Now, my point to that is they're both correct, but the real question is which one seems to be a better choice? And I would say that the one that has been written without the phase shift is probably a better choice of what that graph is trying to say to you. Now let's try these last couple. Example number 7. What are we dealing with here? Well, this is a graph that has been, it looks like it has a vertical asymptote. Okay, ultimately at, I think that's at 3. That's really hard to tell on your deal. And underlying it would be a, check that out, a parent graph that looks something like that. Okay, now that parent graph looks like a sine wave, and that sine wave would ultimately mean that we're dealing with a cosecant graph because it's been turned upside down. Now, I don't know what that's going up by. Man, that is really hard to tell. I'm going to say that that's up by 1. I think that seems like 1, I guess. Amplitude's 1. How far is the wave actually reached? So this sine wave has gone 1, 2, 3, 4, 5, 6. So the period is 6. And that would be equal to 2 pi over b. And if I put that in a cross multiplication, I'd get 2 pi is equal to 6b. And that would be b is equal to pi over 3. And I could put inside here that it would be pi over 3x. And that would be the cosecant graph that we'd be basically looking at there. Okay? All right. I'm glad you got that one under control. I'm not sure if that was, I can't really tell. It's hard to tell what those numbers are. I know. It's not the greatest graph. Now, let's try another one. Let's see if we can get this one. It has been phase shifted. And it looks like it's a phase-shifted, upside-down sine wave is what we're basically looking at. So that would mean it ultimately must be a cosecant graph. So you're like, oh, man, that's a sine wave right out of the way. So it must be y equals cosecant. Seems like the best choice. The amplitude is 2. So I'd be basically 2, but it was flipped. So that makes it negative cosecant. And then I'd be thinking about what do I got to put on the inside here? Now, I would suggest putting the actual b multiplier on the outside and then put your phase shift on the inside. So let's see what we got here between pi over 3. Man, is that pi over 3? Or is it pi over 4? This is really hard to tell. Pi over 3, 2, and it looks like 2 pi over 3, and then pi. Yeah, pi away from that. Boy, man, that is really hard to tell. 3 pi over 3. So it must be pi over 3. So that's a pi over 3 concept there. So I'm going to say it's been shifted to the right, which would be minus pi over 3. And then the amplitude would be 2, and the full entire period is between pi over 3 is 2 pi over 3. 2 pi over 3 is the full period, which is equal to 2 pi over b. and the b value must be 3. So that would be 3 times x minus pi over 3. Now what I'm going to say finally in this video is that graphing is not always a simple concept. So please try a couple of these problems on your worksheets before you get to class and be one of those people that asks, yeah, lots of questions. And make your teacher do a bunch of them on the board for you, help you out, because ultimately your understanding is only going to come from a process of trying. Give it a shot. See you later.